This video is on section 11.4. It's for chemistry and it has to do with stable electron configurations and charges on ions. Actually, in some ways, we've already done something like this, actually several times, but it's a good review. When we're talking about ions forming, there is a fundamental principle for most of the atoms that we'll be working with. There are some exceptions to this, but for what we're going to be working with as we go through the rest of this chapter, we're going to be working with atoms that follow this rule. And that is that all ions seek to be like, or seek to have, I should say, the same electron configuration as the nearest noble gas. And not surprisingly, we call that the noble gas configuration. So let me just show you this real quick because I usually only get about 6 or 7 minutes before I have to stop the video and do part 2. Let's take sodium. Sodium is number 11. By the way, in your book it'll say Z equals 11. That's actually the atomic number. It's 11. And we would write that 1s2, 2s2, 2p6, 3s1. Or we could write this as the noble gas configuration of neon 3s1. Okay. That means that what sodium wants to do is lose this electron. And when it does that, it now has 10 electrons. But it is no longer sodium, and I'm not going to write the 11 here. It's sodium plus 1 because it's lost 1 electron. It has 11 protons, 10 neutrons, and its electron configuration is neon. Basically, it's like neon with a positive 1 charge. If I went to magnesium, magnesium is 12. Again, your book will say Z is 12. That would be neon 3s2. But magnesium wants to be neon, and in order for it to do that, it has to lose 2 electrons, and therefore it'll have a plus 2. And that's called the noble gas configuration for magnesium. If we went to something like aluminum, which is number 13, it's 1s2, 2s2, 2p6, 3s2, 3p1, or neon 3s2, 3p1. But it wants to lose all of those, and so aluminum will take a plus 3, and it has the exact same configuration as neon. If I went to oxygen, oxygen is number 8. And it is 1s2, 2s2, 2p4. But what it wants to be is like neon. And in order for it to get to neon, if we think about this, it needs 2 more electrons. It becomes O minus 2, which is 1s2, 2s2, 2p6, which is the same as neon. And then I could do the same thing with something like fluorine. Fluorine has 9, 1s2, 2s2, 2p5. It wants 1 more electron, and so it becomes F with a minus 1, and it basically has neon. Now I've done neon on all of these, but I wouldn't have needed to. If we took something like barium, which is number 56, that would be xenon 6s2, but it wants to lose those 6s2, so it'll become barium plus 2 so that it's the same as xenon. Now, you are going to do in this chapter a really easy assignment. This is a nice short little video, real easy. We're going to do problems 34 through 40 even in your book. And 34 wants you to do what I've done right here. On 36, they want you just to predict the charge. So you don't have to go through all of this. You can actually just look at the periodic table and do it. On 38, they want you to predict charges of compounds. So they'll say, we've got aluminum, and it has a +3 charge, and you can figure that out by where it is on the periodic table. And oxygen has a -2. What compounds formed? Well, you guys know how to do this from before. We would need to have a +6 and a -6. You say, well, how do I know it's a +3 just by looking at it? I should have had my periodic table up, but your periodic table looks like this. And basically, as we've talked about before, anything in column 1 is a +1, a +2, a +3. When we get over here to our last column, that's the noble gas column. 4 can be either, but normally we do -3, -2, -1, and back to 0 for the noble gases. Sorry, that got kind of messy there. And then problem number 40 asks what noble gas each one is closest to. So they give you this compound, barium sulfide, and they say, what noble gas did barium become? And I just did that one. That would be xenon. So barium has the electron configuration of xenon, and sulfur, which is number 16, ends up being just like argon. So in a very real sense, barium sulfide is like xenon and argon joined together. And that's the idea. The ionic compounds will always end up where you have a noble gas configuration for both elements in there. So read through the section, read through section 11.4, and look at some of those problems. And you are going to do for me 34 through 40. And fairly simple assignment when you start working on it, I think you're going to find. All right, there's one more video that I'll post this evening, and then we'll do more of these, move into molecular compounds early next week. All right, hope to see you soon. Bye.